Welcome to Let's Get to the Marks. Going through the MCQ 2018 AS Chemistry Paper 1. Let's get into it. Okay, so this question is about bonding. Which row shows the bonding in ammonium chloride? And we've got three options: covalent, dative, covalent, or ionic. It can be any combination. Pause the video, have a go, and then I'll go through the explanation. Okay, time for the explanation. So, what we're going to do here is we're going to look at which row shows the bonding in ammonium chloride. We're going to look at ammonium chloride first of all. Well, what is ammonium? Ammonium's an ion, NH4+. Chloride is a negative ion, Cl-. And if we draw out ammonia here, or NH3, we can see that nitrogen's in group 5, has 3 shared pairs of electrons covalent bonded to hydrogen, and then it's got this lone pair. And what happens there, that lone pair is donated towards a hydrogen ion. Do you remember what bonding that is? And then we've got a chloride ion, which has a full outer shell, but it's got a negative charge because it already has an electron, and it forms a bond with the positive hydrogen. So that's ionic. You've got covalent bonding between the hydrogen and the nitrogen, and then dative covalent bonding, where you've got the lone pair being donated towards the hydrogen ion in the NH4+. So it's got all three. So our answer here, guys, is C. Now, just to show you what can happen, if you suddenly get the quibs in the exam and you're like, oh, I don't know if that's right, you can cross it out like that. Then you go for A and you realize, oh, A's wrong, C was right. What do? You circle your crossed answer, and the examiner will then take that as your correct answer. So if you ever cross out the correct answer and then you change your mind and want to go back, circle the cross, and the examiner will know that that's what you want. Okay, this question here, guys: how many protons are there in 6 grams of nitrogen gas? Avogadro's constant is 6.022 times 10 to the 23. 1 mark. Pause the video. Have a go. All right, I'm going to go through the explanation. So look at nitrogen. What's its formula for nitrogen gas? Is it N or is it N2? Well, of course, it's diatomic. So the formula for nitrogen gas is N2. So what do we need to know here? Well, we've been given the mass, right? We've been given 6 grams, that's the mass. And we've also been given Avogadro's constant, okay, which is the number of particles in a mole. And we've been asked to find how many protons are in 6 grams of nitrogen. So there's an equation for Avogadro's, L, Avogadro's constant, and it is number of particles is equal to moles times L. And then we've been given the mass, and you know there's an equation, mass over mR times moles. So you see the link, the N, the moles is the link between the two. So first of all, we can find out the mass of the nitrogen, 6 grams over 28. Why 28? You've got 2 nitrogens. Remember, the mass of 1 nitrogen atom is 14, or 1 mole of nitrogen atoms is 14. So we're going to do 6 over 28. That means that we have got 0.2143 N moles. N is the kind of link between the two equations. So now we're going to times N by L to get the number of particles. 0.1243 times 6.022 times 10 to the 23, which is L, gives us 1.29 times 10 to the 23. A lot of people are going to make a mistake here and put A. A is the correct answer. But of course, A isn't the correct answer, because the question asks for how many protons are there. Now, how many protons are there in each of those 1.29 times 10 to the 23 particles? Well, they're N2 particles, and each one has 7 protons, but there's 2 in each particle because it's a molecule. So there's 14 protons in each one. So we need to times the number of particles by 14, because each nitrogen molecule has 14 protons. So we go 14 times 1.29 times 10 to the 23, and we get C. 1.8 times 10 to the 24 is the correct answer. I hope that helps. Okay, let's move on to another question. This question is about periodicity. The diagram shows a property of period 3 elements varies across the period, or shows how a property of the period 3 elements varies across the period. Which property is shown varying across the period by this diagram? Why don't you grab a pen, grab a paper, have a little study, see if you can work it out, or just do it in your head. Have a look at the pattern and see if you can work out which one it is. And pause the video, and then I'm going through the explanation. So let's look at the first one, atomic radius. So when you think about the atomic radius generally decreases across the period. Now, why does atomic radius decrease? Well, if we think about these elements, well, this is really the ionic charge. You could think of it like that. The ionic charge is getting bigger, but really it's not so much that the ionic charge is getting bigger, because these are atoms, right? We're dealing with atoms, so we can scrap that. We can actually look at the number of protons in each one. So how many protons in sodium? There's 11, magnesium 12, aluminium 13. You get the idea. Silicon 14, phosphorus 15. So as you go across, there's more protons. This means a greater nuclear charge, a greater attraction between the nucleus, electrostatic force of attraction, and the outer shell electrons. What are they going to do? They're going to pull those outer shell electrons closer. So the atomic radius should go down. And remember, there's the same amount of shielding across a period. You're adding electrons to the 3s and 3p orbitals. So there should be the same amount of shielding. So actually, it's not going to be the atomic radius because they've got it going up there. So there we go. Now, when we look at electronegativity, think of the most electronegative elements in the periodic table. They're in the top right. So why has chlorine got lower electronegativity than sodium, magnesium, and aluminium? Chlorine is actually one of the most electronegative elements in the periodic table. It almost can do hydrogen bonding. It's just not as electronegative as oxygen, nitrogen, and fluorine. But other than that, it's got very high electronegativity. So that's definitely wrong. Then we look at the first ionization energy. This links to the atomic radius. How easy is it to remove an electron? Well, as you go across, it's going to get harder because the radii gets smaller. The electrons are pulled in harder to the nucleus because of that increased number of protons, which I've already explained in the first bit. So it can't be ionization energy because it should get harder and harder to remove electrons, not easier as we go on, as you can see the second half there. So the third one, melting point, well, does that follow the pattern? Yes. Sodium, magnesium, aluminium, more delocalized electrons, stronger metallic bonding between those increased positive metal ions and the number of delocalized electrons. You've got stronger electrostatic forces of attraction, stronger metallic bonds. So I would expect that to go up. Then we look at the non-metals, they're going down. Well, there's Van der Waals forces at play here. And yeah, simple molecules, etc. But we have a slight little jump here. We have a slight difference. So we'd expect that. So the melting point's the correct answer. But we've got this slight difference between sulfur and phosphorus that is kind of not expected. You'd expect sulfur to have a lower melting point than phosphorus going across the non-metals, but sulfur is slightly bigger, so it has stronger Van der Waals forces because sulfur forms SA, etc. Right, question 13. A 30 centimeter sample of nitrogen reacted with a 60 centimeter cube sample of fluorine according to this equation. Now, we could go ahead and convert these volumes into moles, but as it's at room temperature and pressure, we can just assume that centimeter cubed is equivalent to moles, so we don't even have to bother. Okay, we can use the volume like the moles when it's over 24,000. So essentially I've got 30 of nitrogen and 60 of fluorine, and the ratio is 0.5 to 1.5 to 1. Now let's make this a little simpler and times it by 2. We're going to get a nicer ratio, easier to deal with. So we're going to get 1 to 3 to 2. Same ratio, 0.5 to 1.5 to 1, but just easier to deal with. So if I have 30 centimeters of nitrogen, it would need to react with 90 centimeters of fluorine. So I don't have enough nitrogen, or sorry, I don't have enough fluorine. Fluorine is the limiting reagent. And in fact, if I want to work out how much nitrogen is being used, I look at that 60 centimeters of fluorine. I know that's all going to be used, but I go, okay, how much of it, how much nitrogen is going to be used? Well, divide the 60 centimeter by 3, and you get 20 centimeters. So it's going to need 20 centimeters of nitrogen because it has a ratio of 3 to 1. So 20 centimeters of nitrogen reacts with 60 centimeters of fluorine. So we don't have any fluorine left over, but we do have 10 centimeters of nitrogen gas left over excess at the end of this reaction. So the next thing we need to know is, okay, well, how much nitrogen fluoride is formed? Okay, NF3 is formed. Well, we want to go from the limiting reactant. Don't use the excess because that's going to confuse you. Use the limiting. So it's in a ratio of 3 to 2. We know all the fluorine's used up, so we're going to get all of that 3 to 2 ratio of NF3. Use the limiting reactant when working out how much product is formed. Always use the limiting reactant. So we go 60 divided by 3, because the ratio is 3 to 2, times 2, and we get 40 centimeters. So we're going to get 40 centimeter cubed of NF3. Add that to the excess 10 centimeter cubed of nitrogen. Yes, what is the total? The total is 50 centimeters, my friend. And that is the correct answer. 13, the answer is D. Voila. Right, 14. Which substance is used to reduce titanium 4 chloride in the extraction of titanium metal? You just got to know this off by heart, guys. So it's TiCl4 plus magnesium, give them away the answer. And that goes to MgCl2 and titanium on its little lonesome. And there we go. Bosh, you just got to know that one off by heart. Get the revision cards out for that one. Okay, question 15. Which statement about barium sulfate is correct? Hopefully you know, is it soluble, insoluble? What do we use barium sulfate for in medicine? What's it used for as a chemical test? So it's soluble in water at 100 degrees. Nah, it forms a precipitate, right? An insoluble white precipitate, and it's used in medicine in the barium meal because it doesn't dissolve in the bodily fluids, essentially. So it can show up on X-rays. It's a pale yellow solid. No, we just said it's a white precipitate. It's part of the test for sulfate ions, SO42 minus ions. Remember, you add BaCl2, um, and they're going to react with SO4 to form this white. Yeah, you get the idea. Yeah, and the last one's wrong because barium sulfate and barium chloride, they're not going to react. Okay, they're just going to swap places if there is any reaction, so they're going to end up with the same product as you had reactant. Right. 16. Which statement is correct about the reaction between concentrated sulfuric acid and solid sodium bromide? So this is about the reducing power of the halide ions, and this is a topic you have on Group 7. So it's the reducing power of the halide ions. Now, if it was sodium chloride and concentrated sulfuric acid, you just get a one-step reaction that's not a redox. So if this was sodium chloride, we get sodium hydrogen sulfate plus hydrogen chloride. But it's not sodium chloride. So it's sodium bromide. And this reaction is not a redox reaction. It's just an acid-base reaction. But what happens here is the hydrogen bromide that's formed in the first step of this reaction goes on to react with some of the excess sulfuric acid, and a redox reaction occurs. And during the redox reaction, the bromide is acting as a reducing agent, and it basically forms bromine. You're going to get the color of bromine, so you should be able to observe that. You're going to get sulfur dioxide, and you're going to get water as your products, and just balance that all up. Now, as the actual overall products here, in questions in exams, they sometimes ask you what's produced as the products. We could say sodium hydrogen sulfate, we could say bromine, we could say sulfur dioxide, and we could say water. Hydrogen bromide is not a final product because it actually gets used up in this second step, this redox step. So the first reaction is just like acid base reaction, right? The sulfuric acid is acting as the acid, the sodium bromide is the bromide ions are acting as a base because they're accepting hydrogen in this. In the second reaction here, what we have going on, we have a redox reaction going on. And if we look at the sulfate ions, they are +4 in sulfur dioxide because oxygen's always -2. And then if you look at the sulfuric acid, they're going to be +6 in that situation. And if we look at the bromide ions, they're -1 and then 0 in their elemental form when they're bromine. So that kind of, you can work that out, that's redox. It's a redox reaction. Don't forget, oil rig oxidation is loss, reduction is gain. Yes, right, let's go through the answers. I'm waffling away and getting carried away down here. Right, bromide ions are reduced. No, look, -1 to 0. What's happened? It's lost electrons. It's become more positive. So it lost an electron. It lost that -1 to go back to 0. So no, they're oxidized. Hydrogen bromide and sulfur formed. Do you see the S here? No, there's no sulfur formed here. But you would get sulfur formed if you used hydrogen iodide because it can further reduce the sulfur dioxide to sulfur. Sulfuric acid acts as an oxidizing agent. Uh, yeah, the sulfuric acid does act as an oxidizing agent, doesn't it? Because the hydrogen bromide's oxidized. It must be the sulfuric acid that's doing it. Bromine and hydrogen sulfide are formed. No, you get the eggy, smelly gas, hydrogen sulfide, when you use sodium iodide, as iodide ions are a stronger reducing agent than bromide ions. And bromide ions are stronger than chloride ions, and you kind of have to know that. So there we go. That's the end of that one. Let's not whiffle, waffle, waffle any more about this one, eh? Let's move on. Right, which compound is used to treat the symptoms of indigestion? This is just a revision card one. You've got to know it off by heart. So it's magnesium hydroxide. It's kind of soluble, a little bit soluble. Magnesium oxide is a laxative, gives you the runs. You don't want to use that just for indigestion. Calcium oxide is a base, obviously. It's a little bit strong and it's not very soluble at all. And calcium hydroxide is very dangerous, very corrosive, very strong base. It's going to like dissolve your organs if you start taking calcium hydroxide. So don't do that. Right, 18. Which element has the higher first ionization energy? So with this one, we've got to look at the orbitals and the subshells. Okay, so difference between an orbital and a subshell: the orbital is the little box with the 2 little electrons in, and the subshell is like 2p, 2s, or 3s, 3p. And the energy level is the 3 or the 2 or the 1. Okay, so this has one electron in its 3p subshell, and that one electron in the 3p subshell is shielded by the 3s2 that's closer to the nucleus. So that's probably going to be quite easy to remove. I wouldn't imagine that's going to have a very high ionization energy relatively to the others. Then let's look at phosphorus. Phosphorus has how many electrons? Bada bada bing, bada bada bong. It's got 15 electrons. So we're going to go 1s2, 2s2, 2p6. That's 10. Then we're going to go 3s2. Then we're going to go 3p3. And the way they fill up is they fill up half, half, half. It's much more stable than having 2, 1, 0. So half filled 3p subshell is extra stable, much more stable than the aluminium there with the little lonely electron shielded from the nucleus. So that's got greater stability. So I'm thinking phosphorus at the moment, but let's check the others. Done this in a weird atomic order. Silicon is got 14 electrons in your periodic table. So if we bust out just the 3p for it, we can tell it's just going to have 2. So that's called a partially filled subshell. So along with the aluminium, that's struggling to keep hold of its shielded electrons from the nucleus, and they're unstable. Let's look at sulfur. Sulfur's got 16 electrons. If we look at the 3p, that's going to have 4 electrons in it. What we get going on here is a little bit weird. We get the extra spin pair repulsion here. And this is often a separate question. They ask you, why does sulfur have a lower ionization energy than phosphorus, even though it has greater nuclear charge and the electrons are being added to the same period, so the same kind of energy level. But the idea is there's extra spin pair repulsion, so it's easier to remove that electron. So the answer was phosphorus. Right. 19. A solution with a volume 500 centimeter cube contains 150 grams of ammonia. So we got the volume. What's the concentration? We want the conc. So we definitely need N over C times V, but they've also given us mass. So immediately your brain should trigger mass over MR times moles. You might say, where's the MR? The MR's in the name ammonia. They expect you to be able to work that out, and it's 17, 14 for the nitrogen, 3 for the hydrogens. So we've got 150 grams divided by 17. The first thing we can do is work out the N. Look at the N in those two triangles. It's the link between the two equations, as it often is. So it's 8.82 moles, roughly 8.82 moles. Now what we need to do is work out the conc. So it's 500 centimeter cubed, but we need to turn it into decimeters. So we're going to do 8.82 divided by 0.5 decimeters, and that you basically timesing 8.82 by 2. So you're going to get 17.6 moles in each decimeter, as you have 8.82 in half a decimeter. And here we go. Alrighty then. Refer to the following information when answering questions 20, 21, 22, 23, and 24. A student devised an experiment to find the concentration of sulfuric acid in a sample of battery acid. A measuring cylinder was used to transfer 10 centimeter cubed of battery acid to a volumetric flask. Distilled water was added to the volumetric flask until the volume reached 250 centimeter cubed. That 25 centimeters of sample of dilute acid was transferred from the volumetric flask to a conical flask using a pipette. A few drops of methyl orange indicator were added to the acid in a conical flask before titrating the acid with the sodium hydroxide. The titration was repeated 5 times, but concordant results were not obtained. Note, methyl orange is red in acid and yellow in alkali. Which suggestion would improve the chances of obtaining concordant results? So we got these 4 suggestions here. Why don't you pause up the video, have a go. All right, extra drops of indicator. I think that one's pretty easy to say. No, that's not going to make any difference. Use more concentrated. Actually, a more concentrated solution in the burette is going to mean that you get a smaller titra. So instead of 20 centimeters to neutralize, you might only need 7. And the problem there is any slight millimeter cube difference is going to be maximized. Like, you're going to have a bigger error. So smaller measurements, there's a bigger error in smaller measurements. Right. What next? Invert the volumetric flask several times after adding distilled water. Well, that sounds pretty good, right? They put in acid, which is going to be at the bottom of the flask. Then you top it up with another 225 centimeters, or whatever it is, another 240 centimeters of water. If you just took 25 centimeters from that, the water's on top. I know it's starting to diffuse and spread out and mix, but the water's essentially on top. So you're going to get not the right amount of moles. It's not evenly spread. So you should put a stopper in and invert several times. You know, it's part of your core practical they're testing you on here. So essentially, in order to get the acid and the water to mix thoroughly, put a stopper in, invert several times. Then when you take your 25 or your whatever 25 centimeter sample from the diluted acid from the volumetric flask, it's a representative sample, right? It should be the same concentration as the rest of the flask. You're not just getting the water from the top that you've just added. So that is definitely going to help you get concordant results. Washing the pipette with distilled water between each titration is no good. No. You don't need to wash the pipette with distilled water. You're just diluting whatever you put in the pipette then, aren't you? You're just diluting the concentration of what's in the pipette. Which suggestion about rinsing the conical flask between the titration would improve accuracy? Should you rinse the conical flask with acid? Not sure about that. If you rinse it with acid, you're just adding more moles of acid to the flask. That's going to screw things up. If you rinse with alkali, you're going to get a reaction, neutralization. It's going to screw things up. You're going to rinse with water. Water is going to ensure that it depends if you're doing washings in between adding drops from the pipette, then that's going to ensure the reactants all mix together. And if it's after and you're going to use the conical flask again, you can rinse with water to get rid of any acid or alkali that's in the flask. Okay, which suggestion would reduce the overall measurement in uncertainty in the titration? So what's going to reduce uncertainty? Use less concentrated alkali in the burette. Use phenolphthalein indicator instead of methyl orange. No, changing the indicator doesn't reduce uncertainty. Using smaller samples. Actually, smaller samples, as I said before, are going to increase your level of error and uncertainty. Begin each titration with a burette. It doesn't matter whether you start at 5 centimeters or 0 centimeters. It doesn't change the volume you've actually added, does it? Use less concentrated alkali. If you use a weaker alkali, you're going to need more centimeter cubed of it. So if I use a strong alkali, say I need 10 centimeter cubed to neutralize the acid. If I use a weaker one, I might need 20 centimeter cubed to neutralize the acid. There's less error in the measurement of 20 centimeters using the same equipment. So if equipment has a fundamental 1% error, 1% of 20 is smaller than 1% of 10. So use a bigger volume. Which of these is important in ensuring the student's experiment is safe? Do the titration in the fume cupboard. You're not really getting any fumes here. If we look at the products of this neutralization, we're not really getting any gases, dangerous gases coming off. So you wouldn't really use a fume cupboard. You're more like with your organic solvents or your aragnic solvents. I've never heard of aragnic, but there we go. Wear gloves. Yeah, that sounds pretty good, doesn't it? Don't get battery acid on your hands, and don't carry a burette horizontally and poke someone in the eye. Okay, final question. Which color change? Yeah, so wear gloves was the answer to that one, folks. 24. Which color change is observed at the endpoint in each titration? So we've got to skip up to the stem of the question and check what they did. They added a few drops of methyl orange added to the acid. So we know methyl orange acid. What color is methyl orange in acid? That's our starting color. So you should know off by heart, put it on a revision card if you don't. Methyl orange is red with acid. Okay, and what color does it goes when neutralized? Now you might think it goes orange, the name methyl orange, right? But it actually goes yellow, and yellow's alkali. Yes, when you neutralize, you go slightly past neutralization point. It's like 0.00001, so it doesn't affect our results accuracy. So it's going to go red to yellow. And I guess it's called methyl orange because red and yellow make orange. There we go. Anyway, guys, don't forget, think about becoming a member. It's $1.99 a month. You get early access to my videos, and some videos are members only for the whole time. And I do Chemistry A-Level live streams, 7 p.m. UK time every Monday night. You might want to join, get some live questions in, and let's learn together. All right, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.